Okay, so all this semester, when we talk about chemical reactions, we refer to reactants making products. That would be referred to as the forward reaction. That reaction is done when you run out of a reactant. Kind of makes sense. We talked about in the beginning of the reaction unit, the chemical change unit, how you have a recipe, you have ingredients. Well, if I ran out of my ingredients to make cookies, at some point I am done making cookies. I've run out of stuff. That's what a forward reaction is referring to, and that's what the majority of chemical reactions that we've discussed deal with. However, not all chemical reactions are like that. Some are a little more unusual. And quite frankly, a theme that I've brought up a few times throughout class is that in Chem 1 we tend to simplify things. Forward reactions are an example of that, that there are a lot of reactions out there that actually aren't just in one direction. It's just a simplification that we bring up in Chem 1 to make the learning a little bit easier and more accessible at this level. Again, the higher up you move in the chemistry chain, the more you learn about, for example, we're introducing equilibrium reactions today. They just don't have a forward direction alone. But that being said, a lot of reactions are this way. That you have reactants, they make products, and that's when the reaction is done. You've run out of something. A backward or reverse reaction is when the products change back to the original reactants. Now, first off, on that packet, when it asks you what is the reactant and what is the product, we will still define a reactant as something that's on the left side of the equation. So for identification purposes, if you are on the left side of the arrow or double arrow, as it were, you are still a reactant. Products are on the right side of the arrow or double arrow. However, what makes reversible reactions unique is that those products can reform the original reactants. Not every chemical reaction can do this. Again, I can't unbake a chocolate chip cookie very easily to get all the ingredients back individually. But in particular, gases are pretty good at having an equilibrium or a reverse reaction, and sometimes solutions as well. And as we move into the next couple of class periods, you'll see more examples of gases specifically and solutions. Okay, so this is the new thing that we're introducing. The fact that products can now go back and remake reactants. That not every chemical reaction is this stuff makes that and we're done. So we have what's called a reversible reaction. We have the double arrow as I show in that bottom bullet point. A reversible reaction goes forward and reverse at the same time. So you have reactants making products and you have products making reactants. And it's not a one thing goes, okay, now other thing goes. This is a constant thing that's occurring. And chemicals do not have thoughts and feelings, and they don't want to have, okay, you take your turn. Okay, now I take my turn. Things are just bouncing around and colliding. Because remember, that's how chemistry occurs, collisions. Things are bouncing around, colliding, and sometimes they can make the product, sometimes the product can go back and make the reactant. So I have one last slide dealing with equilibrium reactions. The last slide's a little more wordy than the rest of these. These are meant to be kind of brief, just what do we mean by forward reaction, what do we mean by reverse reaction, or backward reaction. Okay, we about ready? Okay. In a normal reaction, the end of it is when you run out of reactants. That's what I stated on the first slide. An equilibrium reaction will never run out of reactant or product because reactants are constantly making products, but then, oh, wait, products are constantly making reactants. That doesn't mean that our equilibrium reaction doesn't have an end point, because it does. Second bullet point, at equilibrium, the total amount of reactant versus product is now the same. That doesn't mean that they equal each other. That means there's a balance. Going over an example of one of the Noahs in the back there. If I had $40 in my wallet and Noah had 15, and then he asks for a change for 10, and I give him a 5 and 5 ones, and then I ask him for a change for 10, and I give him a 10, he gives me a 5 and 5 ones, and we keep on doing this back and forth for whatever reason it is. It doesn't change the amount we have in our wallets. We're just exchanging back and forth. At some point, when the same amount is exchanged forward and reverse, that's when we have reached equilibrium. Again, we're going to do a little demonstration here in a bit to show that as well. Again, I know there's a fair amount here, but this third bullet point, when equilibrium is reached, that does not mean the reaction has stopped. Again, elements do not have thoughts or feelings. They're just randomly bouncing around into each other, changing from one thing to another, and then changing back in an equilibrium reaction. So if I'm giving Noah a change for a 10, and then he's giving me a change for a 10, even though the human would say, why do we keep doing this? We're just exchanging the same amount of money. Let's just stop. Atoms don't think that way. They just keep on going. But that's when equilibrium is reached, when the forward and the reverse have balanced out. And that's what my fourth bullet point is saying, is the rate of the forward and the backwards is balancing out. So we're making products at the same rate that we're making reactants. And my very last thing, again, the reaction never stops. I like to sometimes use an analogy of going to a beach as an example. Such a nice day outside, we can only imagine what it's like to go on the beach. And after all, yesterday you woke up and there's snow on the ground. But it brings me back to a nicer time. Let's say I went to a cousin's wedding 15 years ago or so, and it was in Kauai, island of Hawaii. And there you have a lot of people on the beach, but you also have people in the water itself. Now, at any given moment, there are people going from the beach into the water and from the water into the beach. But usually at some point, if you have too many people on the beach gets really, really crowded. And not everyone wants to be really crowded, so they might choose to go into the water. But now all of a sudden, if the water gets really crowded because there's only a certain area where it's safe to swim in, then some people might go back on the beach. And you have this back and forth going until you reach a nice balance. A balance doesn't mean 50-50 balance. A balance just means that the rate of people from the sand to the water is the same as water to the sand. So any individual could change their position, but over time, you have this balance that's reached. And that's what equilibrium reactions are. Equilibrium reactions are when reactants make products, and then the exact opposite happens as well. Now, we don't have a lab in this unit, for this portion of the unit, because a lot of equilibrium reactions are in the gaseous state. Because gases are constantly bouncing around, it's easy for them to bounce around and recreate something else. And we can't do that in our laboratory. So what we are going to do today is when we're done with this slide, I'm going to show you a video that I have the link on for Schoology. That's, again, an analogy. It's not actually chemical reactions, and it's a little silly. That alone might help you remember it. But then we're going to do another example dealing with water back and forth and different colors of water as well, to give you kind of a visual of what it means to be in equilibrium reaction with this back and forth that's taking place. Okay? So that is our goals today, is to introduce the idea of equilibrium to you. Because next class, we're going to now disturb that equilibrium.